It's Farsi, so it means like chaos, but like not in a bad way. So it's like someone who like makes the place lively. So
Let's hope that happens.
yeah.
No.
Okay, so hey everybody, I'm Hengameh. I'm currently a graduate student at Harvard, and I'm giving this talk. The title's a little vague, but it's because I will be describing a few models that they all have interacting dark radiation in them, and how they would potentially address cosmological tensions. And these tensions can be, well, I'm going to simultaneously be talking about both the Hubble tension and the large-scale structure tensions.
Who is your advisor?
My advisor is Matt Reese. But this work is
He's not appearing there.
He's not, yeah. Matt Reese has a very fly from the nest, kind of advising style a little bit. So this work is actually based on, the talk is actually based on two of my works. The first one I actually collaborated with Professor Schmaltz at BU. And the second one is with two of the postdocs. So this first work is usually really the backbone of the idea. So I'm going to be really focusing on this first paper. And if time allows, I'm going to sort of briefly talk about the second work. Right, so I'm going to start by some brief introduction to lambda CDM, which is the standard model of our cosmology. I'm sure everybody here is already familiar with that. Lambda CDM is a great model, and why? It's because the greatness and like how fantastic it is really shows itself when we look at the temperature spectrum from the CMB. As you can see, this is a very, very nonlinear function. And it's very hard to like be able to like this accurately fit this data with only the 6 parameters that are used to that lambda CDM uses to describe our universe. And we also have the another set of data is the matter power spectrum, and you can see the success of lambda CDM model in fitting the matter power spectrum data. Here, our data is a little bit more patchy. We have data from the CMB, we have data from like the weak lensing, and here, which is going to be like the focus of the large-scale structure tension that I'm going to be talking about, we have like the in like the more nonlinear regime, we have the Lyman alpha data that shows up and tells us about the matter power spectrum. And like anything else that is too good to be true, lambda CDM is not without its deficiencies and like without fault. And the two of the most like I want to say important defeats that the CDM is facing is the Hubble tension and the large-scale structure tension. For the Hubble tension, I'm going to get into the details more a little bit, but just briefly, it's the disagreement between directly measuring between the direct measurements and indirect measurements of this of the Hubble parameter. The direct measurements use the distance ladder and cepheids and supernova to measure the Hubble parameter. And the indirect measurement uses the CMB data and assumes a cosmology model. So this is the model-dependent part. And then these two measurements disagree with each other up to 5 sigma. And then the second sort of tension that I'm going to be pointing out to is the large-scale structure tension. And there's more detail to that as well. But if I were to like put it very briefly, is that lambda CDM tends to overpredict the amount of structure for us. And again, something similar happens where if you were to sort of compare the measurements with the CMB data, assuming the lambda CDM, then you get a prediction of structure formation that's higher than the ones that you would get from using the weak lensing data. And in that case, this is a milder tension, but it's nonetheless still there. And this is the data are for the SA tension, but I'm going to talk about a more controversial measurement, which is the Lyman alpha later on in the talk.
So the Hubble tension, has it been moving closer to CMB? Or?
Not on the Adam Reese's group, but there's like, I'm going to get into the details a little bit and show you some data. Not the most recent ones because there's been some development, but we can talk about that after the talk. Okay, so I'm going to just like briefly orient you about the structure of the talk. So
What happened?
sorry, I'm just like looking at the outline. Okay, never mind.
You missed something from the outline?
Yeah, I feel like this. I want to make sure that I'm sharing the.
That's matter, we will forget the outline.
No, it's. One second, I want to make sure I'm, can I like, just make sure I'm sharing the right set of slides, hold on, sorry. Just give me 1 second.
Very good. So now take your time, so. Oh, there we go. Panic. They were the wrong slides?
Yeah, they're
Very
not
good.
the slides. I mean, I had like 2 versions of this and I just realized based on the outline, this is. Okay, this is the correct one. Now let me share it. So sorry about that. There's. Okay. So how do we extend land the CDM?
So there is no outline in this one?
Outline's coming. It's a little. It's a different setup. Yeah. So So after having talked about how great land CDM is and its small deficiencies when it comes to the Hubble and the large-scale structure tension, so how can we change this model to potentially how can we extend land CDM, improve on it to potentially address these tensions? Now I'm gonna try to convince you that adding some dark radiation to land CDM could actually potentially help us to solve both of these tensions simultaneously. And well, as I mentioned, the one part of the Hubble parameter measurement is directly with the data, and the other part is model dependent. So if you want to presumably reduce this tension, we can use a different model, and we can try to modify land CDM either at late times, and by that I mean after matter radiation equality, after CMB has already formed, or at early times, which specifically in this talk I mean between BBN and the formation of CMB. Now, modifying land CDM in late times is actually pretty hard because there's a lot of data, and but nevertheless, people have done it, and there are models who try to address the Hubble tension using late time adjustments. But I'm not going to get into the details of those models. What I'm going to be doing is going to be focusing on early time extensions. And at early times, if you look, the universe is mostly radiation dominated, so it's actually pretty natural for us to add some extra dark radiation. And why is that potentially better than, let's say, early dark energy models? It's because if I add dark radiation, after I pass matter radiation equality, radiation is just going to redshift away, so I don't have to worry about it lingering and messing up my lifetime measurements. However, if I were to add, for example, early dark energy here, I better come up with some mechanism to get rid of that pretty quickly because it doesn't scale and it just stays in my universe at all times. So it's very natural to add dark radiation. If I have dark radiation, the other point is, and another good thing about being in this between BBN and CMB, which I mentioned, is that this is what I call a land CDM, or what we at our group call the land CDM desert. And that's because there are no scales, considering the standard model that we are familiar with, that live in that desert area. So you can basically extend land CDM, add everything that you want, and not worry about messing up any of mixing any of these scales.
The arrows go up. Sorry.
Oh yeah, sorry. It was a little hard to scrunch them, but all the scales are either before BBN or after CMB. And another good thing about being in the land CDM desert is that there's lots of data. So on the CMB side, we are improving both on the large-scale structure data collection and the CMB data. And on the BBN side of things, we're constantly improving on the measurements of the light radical abundance and whatnot. And the last bit, which I guess I sort of skip over here, is that I'm going to talk in detail about this bullet point later, but if I have dark radiation around and it's interacting with my dark matter, it can potentially stop my dark matter from forming clumps and help me address the large-scale structure issue that I mentioned earlier.
But it's not extra degrees of freedom, or you will make them massive?
Yeah, I'll get into the model building of how to do this in a second.
The dark radiation is a dark photon, massive photon, or?
No, it's not massive.
It's something massive.
No, it's not massive. The dark radiation is not massive.
Okay,
It's
so-
radiative radiation.
So we'll not spoil BBN.
Okay, so I'm going to be populating the dark radiation sector after BBN, and there's models that I'm going to talk about how they can do that. But basically, the idea is if you populate the dark radiation sector after BBN, after all the relic abundance and stuff form, then you're not missing anything. And you have this like desert area to like play around with, basically. Okay, so in order to see how these models can fix the Hubble tension, let's dive into the physics of what actually gives us the Hubble parameter. As I said, the direct measurement is relatively easy. It uses the Hubble law, which relates the frequency of stellar objects to the Hubble parameter and the distance of those objects to us. And we're pretty good at, and like, so that being said, if you look at the relation between the velocity or like frequency and the distance of those objects, then the slope basically of this line would give us the Hubble constant. Now, we're very good at measuring velocities or frequencies in cosmology because that just corresponds to us measuring their distance and redshift, sorry, their redshift through frequency. But what's a little harder to do is measuring the exact distance of objects from us. And the further off these objects are from us, the harder it is for us to measure the distance. We're very good at actually measuring objects that are close to us using this method called parallax. But in order to be able to like actually measure the Hubble constant, we want to be looking at things that are very, very far, so that the effect of like them locally moving would not affect the measurements that we're doing. And basically, we want the Hubble flow to dominate over any other velocity. So we want to be looking at very, very far away objects. And the only objects that are far enough and bright enough for us to be able to do that are like these supernova. But since we can't measure their distance from us exactly, we have to sort of look at their brightness and then compare it to the luminosities of the objects that we know. And then this is the calibration part of this measurement, that different groups can use different things. So here, for example, you know the brightness and luminosities of Cepheids, and then you would use them to basically measure the brightness and luminosities of supernova in like further and further off galaxies. And this is what it's known as the distance ladder measurement. And I want to say there are two schools of thought on the Hubble tension, but the one I will be focusing on is the most famous one, is the Shoes measurement by Adam Rees's group, and they use Cepheids as their calibration method, and they measure a value of the Hubble constant of 73 kilometers inverse seconds inverse megaparsecs. And now going back to the indirect measurement, which depends on the model building and the cosmology model that we're using. Again, it's based on a relatively simple linear relation, and it relates the angular sound horizon to the linear sound horizon and the Hubble parameter. Now, let's see, like, what is the angular sound horizon? If I were to look like at the sky, and then I would realize, and then measure the correlation of temperature at every angle, I would realize that at a very certain like angular scale, which I'm going to call theta s, I'm going to start seeing these like very strong correlations between my temperature measurements. And so theta s is very accurately determined by the CMB for us. And then just looking at this triangle, I can see that the sound horizon is related to theta s by like, just like trigonometrics. And this distance is basically how old my universe is, or like how long from the CMB up until now it has expanded. And that's the measurement of the Hubble parameter. And if we do this and use lambda CDM to basically determine what the value of RS is, we get an H0 measurement that is 67.5. And if I were to compare this to the Adam Rees's group, then I get a 5 sigma difference. So I guess in the sense of like, with the question that you asked about the tension getting smaller over time, I guess you can see whether it is or not. Like the error bars are really getting smaller, but like, I'm not sure if the central value like from here on has like really changed.
So Reese is just using Cepheids, right?
He's using Cepheids.
And Friedman, she's using
the tip of their giant branch, but they also recently came up with a third method of calibration.
Mhm.
But I think that Adam Rees's group had like another paper that said that even with this, like when they did their measurements using this new method, they still get what they get, and the Friedman
There's
group.
still a big discrepancy.
there's still, the discrepancy still exists on Adam Riess's group side. And the newest, I guess, thing that I can say is that the Friedman group has came up with a third method of calibration that's interesting and
Has not been used by.
it has not been used so far. Well,
By-
no,
by-
the Adam
by
Riess's
Riess.
group has not used that, no. Yeah. Okay, and then.
So, but when these measurements would fall below the shoes, like closer to the CMB?
She is closer to the CMB. I'm actually forgetting by how much. It's
There's still some signal.
I think there is still some tension, but definitely less than 5. Yeah.
Below the shoes is the floor.
Fair enough.
Good joke.
Usually someone else says that to you.
So now that we know how the Hubble tension is, how the Hubble parameter is measured using the models, let's see how potentially adding dark radiation could fix the issue for us. As I said, the indirect measurement just uses this linear relation, and theta s is very, very accurately measured by the CMB. So if I want to increase the value of Hubble from the 67.5 that Lambda CDM is giving me to 73, which Adam Riess's group is measuring, and I know that theta s is fixed, all I have to do is come up with a, because this is just a triangle, so all I have to do is come up with a smaller value of Rs. Now, what is the sound horizon? And this is a parameter that I told you is model dependent, and it's actually an early time parameter, because Rs just tells me like how much basically the sound horizons traveled from until the surface of last scattering was formed. So if I were to write down, so how much they traveled depends on how fast my universe was expanding. So if I were to rewrite this little conformal time in terms of the content of my universe and the energy and whatever was affecting the expansion rate at the time, I can see that by adding some dark radiation in the denominator here, I would get a smaller value of Rs and therefore increase the amount of H naught that I'm predicting from the model. And this is actually the same way that adding a little bit of dark energy in early times also fixes your energy, your issue, because but in that case, instead of adding dark radiation, you're adding dark energy. This picture is kind of sort of like an intuitive way of telling you why this would happen. And if I were to add some dark radiation, that would cause my universe to expand faster. So I won't have as much time for the sound horizons to travel. So the new sound horizon that I'm going to get is going to be smaller than the one that I would have had otherwise. Okay, now I'm going to basically talk about different types of models and different types of dark radiation that we can add to Lambda CDM. The simplest one is just adding some non-interacting, free streaming, dark radiation, and I'm going to be measuring things in units of the energies of 1 relativistic single neutrino, and this is a run for this kind of model, which I'm just going to call Lambda CDM plus delta N effective. And you can see that it's going in the right direction to sort of reach the measurements of Adam Riess's group, but it doesn't quite make it there. And there are a few reasons why this model might run into a problem. We have to remember that the CMB data is very, very accurate and has a lot to say when we do any sort of Monte Carlo on these models. And adding dark radiation can cause two effects on the CMB spectrum. It can cause free streaming dark radiation, can cause silk damping, and it can also shift the picture here. But yeah, if I add more and more free streaming dark radiation, not only will I dampen the tail of the CMB, but I will also be moving these peaks, shift them. So these two effects are going to make CMB unhappy, and these models are highly constrained by the CMB and not very favored. But as you saw, it was still the right direction. So what we can do to make this better, we can come up with some sort of interacting dark radiation. So it's as opposed to the free streaming dark radiation, this dark radiation is interacting with itself. So you can think of a non-abelian gauge boson or just a 5-4 theory.
Sorry, the reason why there is a contour, is because you make a fit to all the cosmological data,
Right.
And that defines
Exactly. Yeah,
the
that
preferred-
defines You do Bayesian analysis with the Planck data and all the cosmological.
and all the cosmological.
And you vary all the
Okay.
cosmological, the Monte Carlo, yeah. And then you can see that when I have sort of interacting dark radiation, Because the sound speed is lower, I'm disturbing the baryon photon plasma a little bit less. So I'm like all those effects we talked about, the damping and the shifting are mitigated a little bit. So I'm allowed to go closer, but I'm still not exactly quite there yet. So that brings us to this fancy two-component model, which actually has two motivations behind it, I want to say. So one motivation, which I didn't write here, but I'm just going to talk about is, if you look at the CMB data at the low K, at the low L and high L, and then just use like low L data to measure like the Hubble, and then look at the high L data to measure Hubble, then you see that you get like some sort of a discrepancy between the values that you get. So this is called like the little Hubble tension, or the like Planck discrepancy, something like that, if you're like looking at the Planck paper. And this is why a lot of people are motivated to do something when it comes to the Hubble tension, to actually try to add a scale that they can play around with, because it seems like the CMB data itself is actually scale dependent when you like move around the low and high scale. So that's why in this model, the two-component interacting dark radiation, we added a mass scale. And this actually can be UV completed to a West Zumino potential. And that's why we're going to call it the WZDR model, but it's basically just the two-component interacting dark radiation. And let's see what happens at this mass scale. If the temperature of my universe is high, higher than this mass scale, all I have is just a fully interacting dark radiation sector. But as the temperature drops below this mass, then the heavier particle is going to annihilate to the other one. And then what I'm going to be left with is that I end up like injecting entropy and heating up the other sector that I have. What does this mean in terms of the relativistic degrees of freedom that I have? It means that if I start at some like high temperature with some N effective, as I cross this mass threshold, I'm going to increase that N effective. And then this looks like a step, which is why these two-component interacting dark radiation models are also called like the stepped fluid, because like by controlling this, basically the scale, you can control like when you're going to inject energy and increase the amount of dark radiation in your model. This is also another way of looking at it, is that there's going to be basically a time as you're crossing this that you're redshifting kind of halfway in between radiation and matter, and then that's going to help you.
Is the mass of the scalar fixed?
The mass of the scalar is one, basically.
What, sorry?
So you pick it as a free parameter, and when you do Monte Carlos and fits to all sorts of data, then you let it run. And then turns out that the data favors masses of around EV, actually.
EV, okay.
Which is not super, like...
So very close to CMB.
Exactly. I was going to say it's not very surprising, because the only scale that sort of shows up whenever you do any sort of fit to the CMB is like EV. But what is kind of nice is that in this particular Lagrangian, if you let, if you're not interacting with standard model particles and just SUSY is just broken by gravity, then you sort of get the EV mass scale showing up from that. So that's...
the fermions usually, they are massless?
The fermions are massless, yeah. This is just a scalar that has a mass. Yeah. So...
Do you always imagine it to be supersymmetric? Or do you care if it's supersymmetric?
It's softly broken.
It's softly broken SUSY, yeah.
What is it?
M5 breaks.
Yeah, but why do you need the SUSY? Just
Oh, this is just like a way of UV completing it. It doesn't have to be that, but I'm just saying that that's...
you say it's a convenient.
Yeah, it's convenient.
I see, the lambdas don't need to be the same.
It doesn't need to be, yeah, exactly. But I'm saying that it's kind of neat that this happens, but again, I don't know how much you should be reading into it, considering, you know, the fits to the CMB always come up with an EV scale anyways.
So what's the time dependence on the step size as a function of the parameters?
That's a complicated function, but it's in the paper. I can show you.
So it's not simple. There's no simple.
No,
scale.
it's not simple. No. Okay. So unfortunately, the runs that I had included all sorts of other data, including large-scale structure. So from just looking at the picture, you can't just immediately say that the stepped fluid is doing better, which is why I added the table with the Gaussian tensions. So you can see that when it comes to the Hubble tension, the stepped fluid or the WZDR is actually doing better than everything else. And if you remember, some of you might know, there's this paper that basically is called H0 Olympics, and it goes through all the models that are trying to address the Hubble tension, and then based on various criteria, gives them a gold, silver, or bronze medal. And the WZDR paper came out after the Asian Olympics one, but we applied the same criteria to our model. It turns out that we would have gotten a gold medal by the same criteria.
Isn't it a question of how many parameters are in each model?
All of that is taken into account.
Taken into account, okay.
Yeah. Like it's definitely important, like when you're trying to like fit to something, like how many parameters, I mean, of course, if I have like,
Just add one.
3 things to
Yeah.
fit to, and I have like, 4 parameters or something.
I mean, shouldn't the step fluid model have an extra parameter?
It does have an extra parameter compared to, but it's all taken into account when you're trying to, there's this thing called delta AIC, which is like some statistic things that like takes the number of parameters that you add versus how much you're getting from like adding that parameter in. Okay.
So
here's-
what would be the value for the 2.7 sigma that you will obtain? So how much you can improve? Because it's clear that it's
Well, it's
becoming worse and worse now there are other things that are getting spoiled clearly when you go up the ladder, right?
Right,
So what is the 2.7 sigma of what?
so this is just comparing to like the 5 sigma that Lyman CDM was giving you.
Yeah, but I don't know what is the 5 sigma. So is just a knot or is
This is,
or is of all
Right.
cosmological parameters?
right, so when you're doing these fits, yeah, you're not making CMB much worse, basically. So you're feeding CMB, so that's the hard part that each model has to do.
Right, right.
So you're feeding CMB and you're
My
fitting-
question is
getting-
those sigmas refer to what?
Just H naught here,
Just 8 knots.
just H naught.
But what about all the other crap that
Like,
So it's
all the
being
other
spoiled-
parameters are happy, no tension whatsoever.
no?
Like,
Okay.
yeah. all the other parameters are happy, and then you're, I don't know, like, you're doing much better when it comes to predicting H naught than
Okay.
CDM.
Cool.
Okay, here's the outline that you wanted. So just to sort of orient you where we are, so far.
Half an hour.
Well, it's halfway through the talk, so it's time for reorientation. So now we talked about all these various dark radiation models. Hopefully it convinced you that dark radiation is a very natural way to, natural thing to add as an early time solution to the Hubble tension. And we discussed like free streaming, interacting dark radiation, and step fluids. And now we're gonna move on to the second part where we're gonna talk about the large scale structure tensions and how these dark radiation models can potentially address both.
But I'm sorry, but the interaction is very mild. It's just a self-interaction of the scalar field
Yeah.
and a Yukawa interaction of the scalar field with some massless fermions that you introduced.
Yeah, so you basically
That-
want to be considering.
But there's no
one-
interaction with the rest of the world. It's just something.
Yeah,
So
this is all in the
something
dark sector.
that doesn't,
Yeah.
there is no portal to this guy.
There's no portal to the standard model.
Why?
It's all.
So
in the-
why there is no phi square h square for it?
Like wired eye.
Is there anything that prevents that to happen?
Well, I have to think
Okay.
about it, but potentially I don't
That's-
want to mess up any.
But
yeah.
you didn't.
Yeah.
Okay.
Wouldn't you expect it would just be gravitational strength? Or you think something bigger?
Could
Mediated by
be,
something
I
bigger?
mean, could be, but there could be some portal to H. I don't know where this is coming from. Yeah.
You just say, why not?
Yeah.
You're saying
Whatever
why
is not forbidden.
Well, I
is,
mean, I have to think about it,
can
like
be-
both
can be
on the
true.
scale side of things where.
But maybe
everything's-
there's a symmetry or something that.
Right.
Yeah, okay.
I mean, you have massive stuff floating around.
Oh, scalar.
In the dark sector anyway now.
Right, yeah,
At least massive fermions.
math is forever.
There's no light, and the light scalars of order EV.
Yeah.
Okay. So you wouldn't see anything from super radiance. It's interesting. It's too heavy already, I think.
Oh, yeah, super radiant is not yet, no, yeah. But, actually, for my next project, that's actually a very good idea. Good.
Okay.
Okay, yeah, so large scale structure tension.
Okay, now we know.
Now, well, just to, again, just like this, like a more of an orientation style, slide. I'm gonna talk about two sort of representatives of large scale structure. So S8, I already sort of told you a little bit about. So S8 sort of sits about like, at 8 megaparsecs around here. And that, basically what this data is telling us right now, as it is, the tension tells us that Lyman CDM overpredicts compared to this more direct measurements.
So what is that? So.
I have a slide on this
Ah,
thing. Yeah. And then, This is sort of just to give you an idea where S8 and Lyman alpha live on the matter power spectrum. And then Lyman alpha lives further into the sort of nonlinear regime at 1 megaparsec. Okay, so what is S8? S8 is basically a measure of like structure formation. And you have to look at this parameter sigma 8 in the definition. And what is sigma 8? Sigma 8 is basically me looking at my matter power spectrum, delta, and then doing some sort of press vector on it to get the matter distribution out from the matter fluctuations. And it gives me a sense of like structure formation.
It doesn't tell us anything, that formula, because we don't know what delta and W are.
Delta I said is the matter power spectrum.
And W?
And W is is some sort of convolution function. It's a filter that like from, yeah, I mean, I guess I was hoping, anyways, yeah. It's a filter that sort of smoothes out like small fluctuations for me and gives me a sort of quantity that measures structure formation based on small fluctuations. And then on the right, the plot that I have is everything is here normalized by a reference lambda CDM matter power spectrum so that we can see. And the S8 data sort of sits down here, which is 2 sigmas away from what lambda CDM predicts. So if I were to have a model, a lambda CDM, it's like a lambda CDM extension whose matter power spectrum sort of dropped, then I would be potentially able to solve the S8 tension with that sort of model. And turns out, as I mentioned earlier, if I have dark radiation that's interacting with my matter and stops it from clumping, then that would be a desirable model to solve this tension.
But this is a little more complicated than observationally. I mean,
Oh yeah, measuring S8, yeah.
No,
What do you mean?
0.79 is experimental.
Yeah, that's from the weak. That's from the weak lensing. Okay, it's really, there's a little bit of model building involved in this too. So like saying that this is really direct versus indirect, like the Hubble tension, is a little bit misleading. So there's a lot more involved in like measuring S8 from weak lensing versus like CMB. But you can say that these are different data sets. Like, you know, you can have like cosmic shear and weak lensing on one side, and then you can have like Planck CMB and lambda CDM on the other side.
And to go from Planck to what we call S8, there are simulations? Of what?
For S8.
Because Planck,
Yeah, I think.
Planck doesn't measure the large-scale structure, right? The
Planck,
CMB.
yeah,
And
the CMB doesn't
for
know that.
both
So you do, yeah, so for that, like you basically take your model lambda CDM, you fit it to Planck, and Planck is enough to give you the 6 parameters. And then based on that model, you predict, like now that you have like a fitted model of lambda CDM to Planck, then you predict like S8 values and Lyman alpha values, and then you compare them to what you got from like weak lensing measurements of the same parameter. And then that shows a 2 sigma difference. So if I were to change my model,
But
then that would fix it.
okay, large-scale structure is very complicated, right? So
What
it's,
is com-
for instance, there is all the baryon feedback that,
Okay.
so where is all those systematics in these comparisons?
Well, all the systematics sort of show up when you're measuring, when I like report like the sigmas, like all the systematics from both sides are taken into account to like tell you these tensions. And then like they're also reporting in the errors.
Very good, very good. Okay.
The second data set, which we talked about, is the Lyman alpha. And what actually is the Lyman alpha data is you have quasars that are far away from you, and then they are emitting some sort of a spectra at the Lyman alpha like wavelength. And as it passes through the intergalactic medium, you have all these clouds of like neutral hydrogen, and they also have an absorption line for Lyman alpha. So when you look at the spectra that you get, you have your emission spectra, and then you have all these like gases in between, like adding the absorption spectra for the Lyman alpha. So you get this sort of structure, which we call Lyman alpha forest. And based on, you know, how populated, how dense this forest is, you can infer some information about how much structure you have and, you know, basically how much matter you have in between you and the set quasar. And then that gives you information about the matter power spectrum. So the thing about Lyman alpha is that it lives at like 1 megaparsec, which is in the nonlinear regime almost. So the best way that people can sort of deal with that is they take lambda CDM and, you know, do various fits and then run n-body simulations of lambda CDM to be able to extract values that would correspond to the Lyman alpha spectrum. However, the downside is that these simulations can be very, very time consuming. But the good news is on the Lyman alpha side, at least, there's this thing called the compressed Lyman alpha likelihood that tells you the amplitude and the slope of the matter power spectrum at a given scale. Sorry, it's at 1 megaparsec. At 1 megaparsec for the linear matter power spectrum. So whatever linear model you have, you can take your linear predictions and compare it to this like given likelihood. And then that'll basically, you don't have to do n-body simulations to that'll save you time and resources. But basically you can use this like linear compressed Lyman alpha likelihood to compare things with. And what you see, I guess like from here, sorry, is that this is telling you this is where Lyman alpha wants to be, and this is a fit of lambda CDM to the Planck data. And this is telling you that lambda CDM is not steep enough to reach the data that you want. And if you go back to the matter power spectrum plot that had everything on a reference point, then the Lyman alpha data looks like a value and a slope at the 1 megaparsec scale. And again, a model that has predicting less production, less structure for you can basically alleviate the tension here. Okay, now that we talked about both of these tensions, it's a good idea to sort of think about how they play with each other before we jump into model building. And this is kind of interesting that it seems to be the case that Lyman alpha tension like goes in the opposite direction of the H naught tension. So if you were to look at the lambda CDM model simulations, if I try to like get closer to where the Lyman alpha data is, then the values of H naught that would be predicting with the same model actually decreases from what it would be. And then the same thing is true for the free streaming. So if I were to like try to get close to Lyman alpha, again, I'm predicting less H naught. Same thing is true for WZDR, and same thing is true for actually for the early dark energy models in this paper. What they show in this paper is that if they, for all these models that try to like get close to the Lyman alpha data, they're actually the maximum value of the H naught that they're going to get is 67.9. So there's.
So what is the central value? That central value is almost 70. So that we never saw it before, right? So what is this color central value?
Like this
No,
value?
above.
Like this?
Yes.
Oh, so this is just telling you the H naught, like.
Yeah, no, I understand that, but what is the prediction of that? So,
It's not a prediction. It's basically like like a 3-axis Monte Carlo almost. I just wanted to show the trend that as you try to get close to Lyman alpha, then the value of the H naught you're predicting is actually has to decrease.
I understand, but what is the central? So what I am assuming for that?
Oh, you're saying what was the central H naught value for this fit?
Yes.
Okay, I have to go look at the full simulation data.
Okay, what is inside there? So I don't
Yeah,
understand.
I mean, it's
So if I don't have, so far is I didn't put anything in the model.
this is lambda CDM plus free streaming. So this is extra neutrinos like free streaming radiation, dark radiation. Yeah.
That was my question. So
Oh,
you're
okay,
putting,
sorry, yeah, free streaming FS.
you're
Yeah.
putting extra stuff.
Yeah, and then if I don't, then that would be this plot. That's lambda CDM. That's just lambda CDM, but the trend also still exists for lambda CDM.
Very good, very good.
Yeah.
I didn't catch that. Okay.
Okay, so this is I mean, this is obviously model dependent because all of these simulations are model dependent, but at least for like these kind of solutions, there's an explanation for it. And if I were to add dark radiation to my model, as we talked about earlier, that increases. So on the left, you see the temperature spectrum from the CMB. On the right, I have the matter power spectrum normalized by lambda CDM. So if I were to add dark radiation, I introduce silk damping on my temperature spectrum. Doesn't really do much for my matter power spectrum. So you know, when I do fits, then you know the silk damping is going to cause my CMB to be unhappy. So the model compensates by increasing the value of NS to sort of bring this back up here. But now, if I increase NS, my matter power spectrum is going to go up. And then this is why sort of trying to add dark radiation to fix Hubble sort of like makes your large-scale structure issue worse. So if I had an extra parameter that actually allowed me to play around with the slope of the matter power spectrum, then that would be the model that I'm looking for. And turns out that if I just take my dark radiation models, like whatever I had before, and then just couple it to my dark matter, then compared to a cold dark matter scenario, as I said, this will stop you from clumping and introduce some extra pressure and suppress structure formation for you. And if I were to look at the matter power spectrum for this model now, then this is basically, again, this is normalized, but what this tells you is that this part of the matter power spectrum is controlled by the interaction strength of the dark matter and dark radiation. And as I increase that interaction strength, I can exactly control this like a slope. So this is the parameter that we were looking for, the model that would allow us to solve this tension simultaneously. And if I look at my fancier WZDR model and couple the two-component fluid to my dark matter, what ends up happening is at like high temperature. So first of all, like in cosmology, we're always comparing things to Hubble because we're always fighting against like the Hubble flow and Hubble expansion. And during radiation domination, Hubble goes like temperature squared. And the interaction rate of my two-component fluid with dark matter goes like temperature squared as well. So at like high temperatures, this is actually a constant interaction rate compared to the Hubble flow. But as I cross that mass threshold, then I can integrate out my heavy scalar, and then you can see that this interaction is actually dying as I get like cross that mass threshold. So this actually gives us again, the mass scale is giving you that convenient on-off switch on when you want to basically start like suppressing your structure. So if I look at the matter power spectrum now, in addition to the strength of the interaction that's giving me the slope, this is giving me like, okay, when, like it's giving me this horizontal degree of freedom as to like when I want to do this. So I can start doing this early enough that my CMB is completely like unfazed and unaffected by everything. And so now basically I've introduced these two main models, the fluid plus dark matter, or like, interacting fluid plus dark matter, which has 3 extra parameters compared to lambda CDM. It has the interaction strength, and it has how much dark radiation I added compared to lambda CDM. And then I have the WZDR model that's coupled to, the plus stands for them being coupled to matter. So then this guy has that scale we talked about, which translates to some like transition redshift. And then the how strongly my dark matter and dark radiation are interacting, and how much dark radiation I added. And then we did full runs with 3 data sets. We had the main or like D data set that is mostly affected by the CMB, but it also includes Pantheon, BAO, the full shape spectra, and S8 is also in here. And then we have H, which is the shoes measurement, and the Lyman alpha. And so you can see here that the models where dark radiation is talking to dark matter compared to the models where this coupling is not there, actually are able to like cross, and as I increase the interaction strength, I can go all the way down to fit the, to hit the Lyman alpha criteria. And one thing I should have probably mentioned, which I didn't, is that they're actually, so one reason that people talk about the S8 tension and Hubble tension, but no like Lyman alpha tension, is because there's still work to be done on these measurements actually. Like there are 2 sets of measurements for the Lyman alpha spectra, and they are, as you can see, they're not in total agreement with each other, which is why people refrain from saying stuff like Lyman alpha tension so far. But the DESI data is coming out, and hopefully it's gonna like resolve all of the conflicts between these 2 data sets. But you can see that for this is just the fluid, interacting fluid plus dark matter. So this model can't, like if this measurement turns out to be one that's more accurate, then this model can't potentially fit that. But the WZDR one, which allowed you that horizontal degree of freedom, the 1 extra degree of freedom, actually allows you, gives you this degeneracy in the parameter space, so you can potentially fit both data sets if either one of them turned out to be more accurate. So these are just full runs where you can see the green one is for just like basically looking at the CMB and Hubble compared. And then the orange one is CMB, Hubble, and Lyman alpha. And I guess like the lighting is not great, but you can see the Hubble bands over here. You can see the S8 bands over here, and you can see the Lyman alpha measurements. So you can see the orange model is kind of like happily sitting here, alleviating S8 for you, and also the Hubble tension. And then these are the values that you would get for each parameter.
But what is the model? What is M5? What is lambda? What is?
So this is Hubble S8. NL is the slope of the Lyman-a.
No,
What,
I'm
sorry?
asking.
Oh,
are
what
the
is M5?
What are the parameters of the model?
The parameters of the model, so this is how much dark radiation I added, and so, I mean, this is in terms of like
No, I'm
relativistic.
asking the mass of phi is what?
That's still EV.
Yeah?
That's still
EV.
okay.
What are the couplings that you need to add?
So the couplings are, okay, they're measured in a very weird way. I have to convert, but basically they are very weak couplings compared to, I want to say they're like weak, like milli EV or something, like 10 to the -3, -4, something like that. But they're all like.
So these are all dimensionless couplings.
This is a dimensionless coupling, but the
What
thing
are
that
you
we
talking-
actually fit to is different. I have to look at the full simulation.
Ah, okay.
Yeah, and then this is the same one for the fluid model. Is that? And then, yeah, if we want to just like have a better understanding of what's happening on the Gaussian tension side so that we don't have to worry about systematics and whatnot, then we can see that the step fluid actually, so this is the Hubble, which we saw before, but now if you look at the Lyman-a, there's almost 5 sigma tension with lambda CDM. The fluid cuts it down to like 1.3, and then there's like, this is basically non-existent tension with the WZDR model. Okay, so this is basically this part of the talk. How much time do I have?
Like, we started late, so like 15-ish minutes.
Okay. All right. Yeah, so this is this part of the talk, and then I'm going to talk about the second paper that I have a little bit, but not into.
So a new outline?
What?
The same outline or?
No. Just like going into my next paper a little bit. But anyway, so lambda CDM is a good model, but it's not perfect. It's facing like 2 tensions, the H naught and the large scale structure tension. And if I were to add some interacting dark radiation with that's with a massive component, that's my WZDR, the 2-component one, can potentially provide a solution to both of the tensions. And hopefully with future data will help us constrain this more, especially when it comes to Lyman-a, which is a controversial measurement.
May I ask something before you start with the second part?
Mhm.
Chi, the dark matter, right? So you are very so is any dark matter how mass is a WIMP?
Yeah, so
what is that dark matter that you're
right, like so you want the mass of the dark matter to be like heavier than just like temperature at like BBN. That's all. That's all the constraint.
Heavier than MEB.
Heavier than MEB. Yeah, that's all the constraint you have on.
And the second question I have is an obvious one. How do I ever test this? Because you're
yeah.
putting something that is very dark and is not
Yeah, it's all in the dark sector.
all in the dark.
Yeah.
But how?
guess
How do I
we-
know that this is the model? Then,
Just give it some small coupling with the Higgs, and then you can test it as a.
right.
I mean, yeah, that's why you were asking for connections to
Right,
general.
I was
Yeah,
asking some portal, yeah.
yeah, you need to have some portal. Other than that, like you're left with like inferring data from tensions and whatnot.
Yeah, exactly. So, okay, very good.
Yeah. Although if you have, if you tune up so I talked about the regime where the coupling between dark radiation and dark matter is very weak. And then I'm coupling the entire dark matter weakly to this like dark radiation.
Right.
But there's another regime where you couple a fraction of your dark matter very strongly to this dark radiation. And then what ends up happening is you get like dark acoustic oscillations in your matter power spectrum. So that would be a very, very distinct signature that tells you about the existence of dark radiation in the dark sector.
But this is not this model. so-
Not this one, no.
Very-
But dark radiation can have like that very distinct signature
Very
that
good.
shows up in different regimes of
Okay,
what I
thank
talked
you.
about. So okay, that was in case I didn't have enough time to talk about the second one. But okay, so we sort of took the same idea, and I talked to you about how having these like sort of like dark radiation, dark matter, like could potentially alleviate tensions. So in the second paper that I have, we sort of thought, okay, axion is a very like interesting dark matter candidate. So can we do potentially something that relates axions to these sort of cosmological tensions? And the setup of this second model that I have is sort of, we have a dark plasma of dark photons and dark electrons. And we have axion dark matter, but it's a dark matter that's actually very, very light. So we want the mass of the axion to be much, much lighter than the temperature of the bath around it. And in order to generate these sort of dark matter, like I think it's like kind of like special for axions because you can generate them like non-thermally through like various mechanisms like misalignment. And then we call this sort of dark matter like the axion condensate in our paper. And so what it basically is, it's an oscillating axion field, and an oscillating axion field can be sort of regarded as dark matter for you because if you look at the evolution of the equation of state for this axion, as the universe like evolves, and then the Hubble scale here drops below the mass of your axion, then well, before then the Hubble friction is sort of holding you in place, so you're just constant everywhere. But then, so you're like dark energy basically. But then as the Hubble parameter goes below this mass, then this term starts dominating in your evolution equation, and then you start oscillations. And then on average, you're basically behaving like matter. So this is the idea behind this oscillating field, axion dark matter, and then we couple this axion to the photons in the plasma. And if you look at the interaction rate, so if you look at the interactions that axion has in the plasma, basically because we took the mass of the axion to be very, very light, the sort of the 1 to 2 process of your axion evaporating and like decaying into dark photons is basically forbidden. So this is not happening. You don't need to worry about this. Kinematically, your axion doesn't have enough energy to evaporate into the dark photons. And then for weak coupling contacts, and I should have probably added it here. And for like, I mean, we're talking about light axion masses as well, but turns out actually around like order here, like less than eV basically, like because all of this stuff is happening around CMB. So as long as you're like lighter than the temperature square, like scale around that time, you're fine. So for light axion masses lighter than eV and light couplings and weak couplings of the axion to the dark photon, the process that actually dominates is called the Primakov process, is the one that's dominating. And the rate of this Primakov process, you might naively think goes like temperature cubed because that's the density of.
What is EV? What's the?
Dark electrons.
Oh.
In the plasma I mentioned earlier, we have dark photons and electrons interact. And then you might naively think that your rate goes like temperature cubed because that's the density of the electrons and stuff in the plasma. But actually, because this axion has a very high occupation number and it's a condensate, you get this like stimulated production like sort of factor that shows up and then like changes this into a temperature squared. And why is the temperature squared very important for us? This sort of goes back to like my last slides where we were saying that everything you're comparing to the dependence of Hubble during radiation domination. And because Hubble goes like temperature squared, then this means that you get the interaction basically remains constant for you in radiation domination. And then afterwards, it may or may not drop, but like it definitely dies off when you enter into dark energy domination. So what does this tell us? What does this interaction, what does having a constant interaction in radiation domination tells you? If I look at the Boltzmann equations of my cold dark matter axion, so here my dark matter is redshifting like dark matter, I have 3H, but then I'm sort of evaporating this axion at this temperature squared rate. And then on the dark radiation sector, I'm injecting whatever I've like evaporated into the dark radiation. In photons. So what does this mean is that during the radiation domination, I have no matter. I have no like matter is subdominant compared to all the other energy components. So I basically am not generating any extra energy here.
Is axion mass larger or smaller than temperature?
Smaller than temperature.
Smaller than temperature.
Yeah.
So it's then suppression of the Primakov rate rather than the enhancement.
Right. Yeah. Otherwise you don't get that stimulated in an enhancement factor.
Sorry, did you say enhancement or suppression? Sorry.
But it suppresses it's kind of like the inverse of a stimulated emission process. like you would think that it cannot gain any, you would think that nothing, basically everything is like too hot to produce like something as cold as your axion condensate for you. But because it's a high occupation number, there's actually a small fraction that ends up happening anyways. Like compensating for the small phase space is the large occupation number of your condensate.
That's the data from dissipation rate, the oscillation particles, when the particle couples to gluon or photon, for which people find just T cubic over F squared without a suppression by the mass divided by temperature.
Yeah.
I just confused why you have a suppression factor here.
Like,
Could you show again the formula?
yeah, I'm saying, yeah. So this sort of, I guess if I want to explain is, if you were to write down like all the Boltzmann stuff, you know, because, okay, when you're doing the Boltzmann thing, this rate goes like, you have like a minus like n or whatever, times like you're integrating over all these like f factors, right? But then you usually have over here like a plus n, and then you're integrating over all these 1 plus f factors. Usually, when you're not dealing with condensates and like, you know, you can say that this f is less than 1. So usually you're ignoring this and then just like integrating over the first part, and then you get suppression factors. You get like some rate. But then because this has a very, very high occupation number, then f is not small compared to 1 anymore. So you have to include the second part of this integral. And then what this ends up giving you is that your rate compared to what it would have been without the thing times some, like the chemical potential stuff comes in, and then you get something that's like the mass of the axion over the temperature of your bath, so temperature of the dark sector minus 1. So this is a suppression factor that shows up. So if your axion is very, very light, then this gives you an m pi over temperature squared suppression. And you can basically ignore it if your axion is like heavy or something.
So if this is really the suppression factor, I'm just confused. This action couples the photon, and this just maintain some shift symmetry action, which means this matrix element receives suppression by the action mass square.
The matrix element is untouched. The matrix element is here, right? Like when you're integrating these things, like the matrix element is here. And then you're not touching that. Like this suppression is just purely coming from the phase space factors.
Yes, but my claim is, first of all, before even talking about the suppression or something, that my claim is a naive rate before taking account this factor, it should be suppressed by m squared divided by t squared. Because matrix element itself is suppressed by this derivative on the action, which is roughly this, you're talking about oscillating actions, which should give provide m squared.
It's not that, because it's coming from this exponential. It's not coming from the matrix as you're thinking. And this exponential, you know where that comes from? That comes from like, you have all these like occupation numbers of like the particles that are involved in your like process. Like this is the Primakov that I'm looking at. And then if you take the ratio of like, let's say you have like, you know, N1 incoming, N2 incoming, these are like number densities of the incoming and outgoing particles, then you have like N1 outgoing, N2 outgoing. And then if I were to factor this out, then the N1 outgoing, N2 outgoing or whatever over like N1, N2, like this ratio.
That is equal to 1. No,
No, it's not one, exactly.
You wrote the same above and below.
Sorry, what? Oh, sorry. You're absolutely right. The ratio of this incoming and outgoing is actually going to be like exactly like off by the emission of this like very, very soft axion. So this is going to give you like the exponential of like m pi over the temperature of your dark sector. This is where it's coming from. And it's really something specific to when you're dealing with condensates that are really, really cold and just like sitting there. Which is why I'm saying it's kind of like a stimulated emission thing that shows up when you have like condensates and like Bose-Einstein like statistics. It's not there when you're dealing with Maxwell-Boltzmann.
I understand, but I just wondering where this the m squared from the matrix element go.
like that goes into giving you this T cubed factor, like all the way over here, this is untouched, and then you just end up with this extra suppression that multiplies everything else at the end.
Okay.
There's a Weinberg paper I can show you that discusses this in like actual detail, like how to get this, like why this suppression factor shows up when you're dealing with something that's out of the equilibrium with the rest of your plasma and has a very high occupation. Okay, so with this T squared, we're constant here, but there's no matter, so we're not generating any extra injected energy. And then over here, we don't have any, well, any amount of like sort of dark radiation that we've evaporated and generated is going to be redshifting like 1/4, and it's going to be subdominant. So basically in this model, we're like injecting energy right around matter radiation equality, and it's basically has that quality that we talked about, that you want to be addressing really things in this like small window if you want to address the Hubble tension. So in this model, then we looked at, so we didn't do any runs for this model, it's just the idea of the model. But on a very like sort of first level estimate, you can show that as you increase the interaction rate between these axions and photons, so like the evaporation rate basically increases. Because you're generating this dark radiation around matter radiation equality, then the prediction for the Hubble constant goes up. And then, so you can potentially hit the bounds, which are not, I guess, like the 1 and minus sigma over here or here, but these are the rhesus measurements. And you can see that you can potentially address the Hubble tension with this model. And then another way of looking at it is, if I start with because I said I don't want to like populate my dark sector around BBN. So if I start with, one way to address the Hubble tension is I add a lot of dark radiation around BBN, but then that messes things up. But in this model, you don't have to start with a big amount of dark radiation, because if I just increase the amount of evaporation rate, by the time I make it to like matter radiation equality, I can give you the same. So in this plot, Hubble is fixed to 73, I guess. Sorry, it's fixed to the value of rhesus measurement. And then I show that, in this model, if I just crank up the evaporation rate, I don't need to start with a big amount of delta N effective, because by the time I make it to matter radiation equality, I can just generate the amount of dark radiation from dark matter. Okay, and then the part that we're still, I guess, like thinking about is whether this dark matter can, like, the abundance of this dark matter, whether it can be the entire dark matter or not, and that's still part of the work in progress. Okay, that's, I guess, it.
Question? I mean, other than what we should.
How sensitive was this to like the specific model that you picked for the radiation? Like you said you used a scalar, but like.
It's not sensitive as long as the radiation is strongly self-interacting and acting like a perfect fluid.
So the fact that you're using bosons doesn't matter at all.
No, as long as they're like, as I said, you can have a 5-4 theory or you can have gauge bosons. Well, I guess they're both bosons, sorry.
Yeah.
But like as long as you can look at them as a perfect fluid, which is the description you're using in your Boltzmann equations, you're fine.
Yeah, and okay, good. I guess like you only care about like the thermodynamics, so like the fact that you have bosons versus fermion doesn't matter.
Doesn't matter, yeah.
Yeah, I can ask one quick question. I think I just missed something back in the first part of your talk. It was like, you like to like, it was like 14 or so. ish.
Alright, this is
No worries.
for animation's sake, every slide is like 10.
Yeah. Sorry, I was just confused by something that I think you explained, but I missed why the equation of state parameter after going down then goes back up again.
So if I go back here, so when you're in this transition area, you're a little like halfway in between matter and radiation. But then when you're all the way over here, then the psi particles are just interacting with themselves. So you just have like this vertex because you want to remain as a perfect fluid both before and after the transition.
Okay.
So then you have to start as radiation, dark radiation, and then end up as dark radiation.
Excellent. Okay, great. Thanks. All right, if there are no more questions, let's thank our speaker again.